Yeah, anyway, so that's me. Yes, we can start. Or can we? Have you, like, the ones who want to follow along, you've gotten the installation mostly done? Very good. Okay, so that's that. Part 0, the data. Prerequisites. So this first part is just going to be sort of a very quick general introduction to neural networks. There's a data set that we'll be using. It is in German on purpose because I want you to get yourself into the mindset of thinking about natural language and applying these methodologies to languages other than English, because there's various different sort of problems that arise when you're dealing with languages other than English. And it's useful to have those in mind. I have some examples of those later on. There's a ton of links. I've tried to make sure that they're all to open access journals, so you don't need to log into anything or be an institutional subscriber or anything. You should be able to just access all of the research papers that I link to in the presentation. So prerequisites. Neural networks have, in general, let me just start a timer for myself. There we go. 4 parts. There's the network architecture. Whether you're using a feed-forward neural network or a recurrent neural network or a transformer or convolutions or whatever. How deep the layers or how deep the network is, the layer sizes, how they're connected, all of that. That's the network architecture. But there's a bunch of other things that are also important. There's the optimizer, the algorithm that you use when data is passed through the network and you have some loss function. The optimizer then, given the loss function and the gradients, the optimizer will actually do updates to your network parameters. And it is not, it's not an insignificant part of how the network learns. Because the network architecture itself is just a static thing. The thing that actually makes the trained network have some utility is the fact that the optimizer has done all of these adjustments. And there's a whole bunch of different kinds of ways of doing that. There's a quick overview of how that works. Then there's a learning rate scheduler, which in the NLP community has become relatively significant as well recently. So the idea is that you don't just use a single fixed learning rate throughout the entire training, but you have a schedule that changes what the learning rate is depending on where you are on the learning cycle. This is especially important for as the networks get, so the intuition kind of behind this is that as the networks get deeper and deeper, you want to have some kind of a schedule to that, so that right at the beginning, when the network hasn't seen a lot of data and hasn't learned a lot of things yet, you have a very, very small learning rate, so you're doing small kind of incremental adjustments until you get to a somewhat more stable state, and the network has been able to, ideally, sort of propagate some kind of wisdom throughout the network. And then you can start sort of making a slightly more larger adjustments. Hopefully you won't need to anymore, but that's the idea. And then, of course, there's the learning objective or the loss function, which is completely problem dependent. Can be a document classification problem, as is the case for this tutorial. Can be some language model, some unsupervised thing. There's various different kinds of language models as well. It can also be some other token level classification task, like, I don't know, named entity recognition, for instance, and these loss functions depend a little bit on exactly what problem it is that you're trying to solve. The PyTorch documentation itself contains quite a lot of reasonably good tutorials with downloadable notebooks on NLP as well. So I recommend that you go and look at those afterwards. Okay, network architecture. Is the font size okay, by the way? Can you, the people in the back corner there, you can see what's on the board? No one protests, okay. So this is a simple feed-forward neural network. And this is in PyTorch. So what happens is there's a definition of what the network is. This is not how it needs to be implemented. This is just a decision that I have made on how to implement it. So there's a layer spec, which you will see later what that contains. And then there's a list of modules. Each module in that list of modules is just a linear layer with some number of features coming in and some number of features going out. And the numbers of features coming in and going out are both contained in this layer spec that is passed into the class. Ideally, you would also initialize the weights, but I've left that out for the time being. And then there's an activation function that is applied to each one of the layers. There's a forward pass. This is kind of a specific thing for PyTorch. You write your forward passes yourself. I find it useful because it both allows you to think, but it also forces you to think on how exactly does the data pass through the various different layers in the network. So what comes in is some instance X. First we have no output, then we start going through all the layers that we defined earlier. We pass in the first instance just the X through the layer, and then the output of the layer through the activation function. Store that again in the output, and then on the further iterations, we pass the output of the previous layer into the next layer and sort of keep doing the same thing over and over. And you can add dropout, you can add blah, blah, blah. This is just a simple feed-forward neural network. And then last, we apply a log softmax that just turns whatever the network predictions are into some kind of probabilities and return that. So then we have two classes, arbitrarily, some number of features, and then this is our layer spec. So we have n features, 50 coming in. So our bottom layer is going to be 50 features. It consumes vectors that have 50 elements, and it outputs vectors that have 25 elements. And then the next layer takes the output of that and then outputs a vector that has one entry for each of the classes that we're interested in. And now I should be able to run that. Right, so we create our feed-forward network. We have some random data that we feed through that. This is completely arbitrary what we're doing here. But you can see what happens. So we have inputs which are just random numbers. 10 examples of 50 features each. And get probabilities back. Or something that looks like probabilities. But as you can see, if you take sums over these rows, you can see that everything sort of sums to 1 because the network hasn't actually learned anything. All the weights are random. All the data is random, so you get back just a uniform distribution over the classes. And this, we can change this arbitrarily. We can set that to 100 features or add new layers here, whatever. Right? Is that sort of roughly okay? It's the reason I'm sort of laboring this point is because there's a number of cases where you need to look at this same kind of pattern. You have a network definition, and then you have the forward layer. Any questions about that? Yeah.
The only question is we haven't called the forward layer.
We've called the forward layer here. So we first create the network. This feed forward constructor calls the init.
Yep.
This FF, this is just a PyTorch sort of specific thing.
Okay.
So you created an object. This object is callable in the PyTorch world.
Okay.
And when you call it, it first passes through a bunch of stuff, internals in PyTorch, and then eventually it ends up in that forward call.
Cool, thank you.
Any other questions? Okay. Optimizer and scheduler. Sebastian Ruder wrote a very thorough, very good overview, I think it is here, yes, of gradient descent optimization algorithms, gradient descent in general, and then the optimization algorithms for that. This is, if you want to know exactly how they work, this is very useful to read. But this is a reasonably long post, so I'm not going to go through this in detail. The idea in general, so we have gradient descent that just does an update to the weights given a learning rate, or like weighted by a learning rate. There's stochastic gradient descent, which then does an update after every single example, after every single instance has been passed through the network. So in the previous example, we would do 10 updates with stochastic gradient descent. And there's mini-batch gradient descent, which is kind of the same thing, but instead of doing the update after every single iteration or every single instance, you batch the instances into slightly larger groups. The idea is that when you batch the instances into these larger groups, it allows you to, when you're measuring your loss function at the end, the fact that you've passed a little bit more data through the network gives you a slightly better understanding of what that error gradient looks like. You have a better sample, given your data, how to do the parameter updates. And the size of that mini batch is in some cases also quite significant for the learning itself. But it's dependent on, again, if you're running these on a GPU architecture, you can only afford to do mini batches that are small or large enough to actually fit into the GPU memory. So if you have a GPU with 16 gigabytes of memory and your network architecture already itself takes, 12 gigabytes, well then you can only do mini batches that fit into that 4 gigabytes. Or 3, because then you need overhead, blah, blah, blah. The idea also with stochastic gradient descent and mini-batch gradient descent is that they use the same parameter update, the same learning rate for all parameters in the network. And then you have these adaptive learning rate schedulers, or optimizers rather, Autograd, RMS Probe, Atom, RAtom, Atom W. The idea here is that, well, not all parameters in your data set are equally frequent. So you want to adjust the updates that you do based on how often you've seen certain kinds of patterns. So the adaptive learning rate optimizers have some inbuilt sort of mechanisms that allow you to do that. Or, well, they don't allow you to do it, they do that for you. There's something I need to say about this. Oh, right, okay. So Atom used to be very popular. I think, I don't exactly know where things are heading at the moment, but it seems to be that this RAtom, rectified Atom, or an Atom W are reasonably popular at the moment. But that might change in, 3 weeks from Any questions about that? Okay. Training the network. So we load some data. There is a, yes, okay, sorry, this is not actually loading any data. So this is just random Gaussian data from, there's a data generation function in sklearn called makeBlobs. What have I done here? I think two Gaussians, 500 samples, some number of features, this we said before, and we have two centers. We do a training and test split, then we create tensors out of those. We have a random sampler that takes random samples out of these tensors. We have a data loader that sort of ideally moves data back and forth and sort of does batching, right? We have a batch size of 8 now. And then we have a learning function, right? Remember in the example previously, we just did a forward pass. We didn't do any parameter updates. So we have a learning function, train model, blah, 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 some bookkeeping for recording the losses. You go through some number of epochs. You zero out the gradients in the optimizer. You set your training loss. This is just bookkeeping. And then for all of the data points, you do a forward pass through your model. You measure whatever the loss was on that model and that data. You do some bookkeeping. You back propagate the loss. This doesn't do any parameter updates, by the way. This just updates what the information that is required to do the parameter updates, but the parameters are still left untouched. Then you update the parameters. And then if there's a scheduler, you update the scheduler. And again, you zero out the gradients because these gradients accumulate. This is PyTorch specifics again. And then you do some bookkeeping. So we have a feed-forward neural network. We have a loss function, negative log likelihood loss. We have an optimizer. We're just going to use SGD, but we set the learning rate to that. There's a lambda scheduler. This doesn't actually do anything. This is mainly just there to illustrate how you sort of create one. This is just a fixed learning rate of that. Train the model and see what comes out. And that doesn't work. I forgot that I had removed that.
I got the arrows.
Yeah. I think IE.
Where is iStep? iStep is there.
In default, we need to find the IE part, but not iStep.
No, this should be iStep. Hold on. This is easy to fix. Okay, so you need to start the iStep from 1, because otherwise you'll get a division by 0 error here. Well, or you can do +1 there, however you choose. So that's a trained model that seemed to have run now. And now we are recording the losses from various different, what did I do? Optimizers, right? So there's stochastic gradient descent, and then there's Adam. So stochastic gradient descent for this number of epochs, you don't really see. I'm pretty sure this goes down a little bit, but you don't really see that. For stochastic gradient descent with momentum and Adam, you see that the loss on the, I think this is on the training data, the loss on the training data actually goes down reasonably quickly. So you're learning something, right? This is, the only point that I'm trying to make here is that the optimizer actually makes a difference. Right, we haven't done anything with natural language yet. We just had random data. So let's do natural language. how do we turn natural language into something that we can feed into the network? Who has heard of word vectors? I think everyone. Okay, awesome. So we turn the natural language into word vectors, and for this we need to load the word vectors. This is just downloading them. You should all have downloaded the word vectors already. This is loading them. I'm gonna try to at least load the small file, which is not in the downloads, it's only on the USB stick. So if you don't have that, you can load the big one as well. It's just gonna take longer and take more memory. There's a ton of stuff written about word vectors. If you need to know more, you wanna read more context on that, here's a bunch of links. That's still running. This is kind of the general idea about word vectors. So you create you create an embedding, you create a vector for each word that captures some distributional similarity, some contextual information on in which kinds of contexts does that word appear in, and you want the vector to be some kind of a representation of that. This is just taken from the original Word2Vec paper by Mikolov. You could do continuous bag of words where the idea is to predict the word given the context, or the other way around, you predict the context given the word. There's a whole bunch of other word vectors. I think what I did is, yeah, these are the fast text word vectors. Okay. And I'm sure you've all seen this task. So the idea is the word vector class in GenSim allows you to do these similarity calculations or sort of tasks. But let me just load the English ones as well. Remember, this is the vectors that you have there are German vectors. So the vector that is closest to Berlin is Potsdam, which is a town just outside of Berlin. Charlottenburg and Neukölln are boroughs inside Berlin. Hamburg, you probably all know, Brandenburg is the state where Potsdam is in, and so on, right? So whether or not these word vector sort of similarity tasks do exactly what you expect them to do really depends on what data they've been trained on. I hope this loads quickly enough so that I can show you this similarity task on the English and the German word vectors. Questions? Can someone have one question while this is loading?
So what do you do with word vectors in the neural network model once you have that?
So the idea is that you, instead of doing what we did here before, where we just fed in random vectors, the idea is that you use those word vectors as your word representations. So you create a dictionary essentially, which just maps word indices, global word indices, into their vector representation. And then that's fed into the network. There's an example here. I'll just let that load. So there's an example here, feed-forward network with embeddings. So what we do is we have this exact same layer spec that's coming in. We have this exact same layer definition that was in the previous one, but there's an additional thing that is the embeddings. This embedding layer comes from PyTorch, and it is just a lookup table. It takes word indices and turns them into vectors of vectors, essentially, where those initial vectors are the word vectors. Okay, that's going to load at some point. And then, so that's the network definition. And then the forward function changes, of course, as well, because we need to pass the x first through the embedding layer. This turns, so this x now contains integers that represent word positions in some global dictionary. And that embedding layer turns those integers into the vector representations. It just does a lookup from the table that it has. You need to do a little bit of sort of shifting of the results that you get back, but that's not relevant to this thing. So you get an embedding back, and then you feed the embedding to the layer, not the original image. We load some training data, load the Spacey tokenizer model, define a tokenization function. What's important here is this. So before, we didn't have to worry about the length of any input data that we have, but of course natural language doesn't come in sort of nice, similarly sized pieces of text. Every document, every sentence, every utterance has a different length. So we need to do something about that. Now that thing has loaded, so I'm just going to skip back quickly and show you how this works, because I thought this was quite fun. Right, so in English, the most similar to Berlin are actually other cities, not boroughs inside Berlin. And then you can do that as well. I don't know why that happens in German, but that depends on the training data. In English, the most similar to Python is Python. Okay. Right. So this task you have presumably all seen. There's a mystery. So this is convenient because you can do arithmetic with this. So we take the vector for Berlin, we take away Germany, and then we add France. I heard someone whisper Paris. Does anyone have any other suggestions for what's going to come out of there? Everyone's happy with Paris. Not exactly. Yeah. And then you can do the same thing with the English ones, and you get a slightly different song. But again, these are not like, you shouldn't think of the word vectors as some kind of a ground truth, that if you have pre-trained word embeddings, they're just going to always correctly do the thing that you want them to do. Whatever that representation is dependent on the data that it was trained with. And if you use different word embeddings, you might get different results. You likely will get different results. It depends a little bit on what your task is. And so finding out what exact embedding is the correct one for your task requires you to just test which one is the correct one for your task. But there's luckily an abundance of word vector, different kinds of pre-trained vectors that you can download. Okay. So where were we? Tokenize. So we truncate our text. Run through, sorry, let me try to load these because this is going to take a while again. Right, so we tokens, we get some message, we run through each of the words in the message, so pass the message through the tokenizer, run through the text, blah, blah, blah. And then we turn this into word indices, right? So we don't have tokens anymore, we don't have text, now we have integers. And crucially, we do this truncation. So we just say our documents are now 100 words. And because we've said that the documents are 100 words, if the documents are shorter, we also need to pad them. We just say that, well, anything that goes beyond 80 words will just replace all the rest with some special pad token. This word index is created here. We add one to the, so we take everything from the word vectors itself, but we add one to all of the indices because we need that one extra space for the padding token. And then we encode the labels as well. Okay. Hopefully that's not going to take too long to run. Do exactly the same thing with the data. Turn it into tensors. But now our layer spec needs to change again. So before we had a layer spec where the input layer was 50 tokens. Now we have 300 dimensional word vectors. Did I remember to do this? Yes, we have 300 dimensional word vectors. So every single word will create a vector of 300, of length 300. But we also said that we're going to truncate our documents to 100, or in this case to 25. So we need to account for that in the bottom layer, right? So the bottom layer input is actually 300 by 25. And then you do the same thing again, and then the output is just however many classes happens to be in our data set. This data set contains, I think, 9 classes. Create the layer spec, and we get an error. Oh, I forgot to actually run this. This is going to take quite a long time to run. I'll just stop it soon. This is also not going to do anything particularly useful. The point is not to actually create a useful predictor out of this, but just show you how the word vectors are actually fed into the network. So let's stop that. That can go away. And we have some, is this actually set? Yeah. So what is this output? This output, where did that come from? I don't know, doesn't matter. Maybe this is not relevant. Ah, no, here. Output. Output is the output from the feed-forward neural network. This is, right? But this is whatever our batch size was by the number of classes that is in the data set. Make sense? Okay. Now, that seems like a rather simplistic thing, but word vectors, like just sort of simple concatenations of word vectors, tend to work for some document classification tasks really well. The fast text embeddings come from this paper, and they show some pretty good results. We run in production these models, like the fast text classifier models, and they're fine. They're like, it's worth trying. Okay. Well, half an hour is gone. Part 2. Recurrent neural networks. Unless someone has any questions about that. No? Yep.
Maybe just on the word embeddings. So is the point of word embeddings sort of like a feature reduction step or feature generation step, in that you're trying to reduce your total number of your total vocabulary down to a smaller set of descriptive ones?
Right. So the question is the point of the word embeddings to somehow reduce the dimensionality of the feature space is what you're asking, right? Okay. No, that's not the point. The point is that the word embeddings capture, so if you look at this graph, the point of the word embeddings is to create representations of individual words that have 2 properties. One, they are arithmetically, like they fit into the world of linear algebra. And we can do arithmetic operations with them. We can add them together, we can subtract one from the other, and so on. But the other important property is that they contain some kind of a semantic or some kind of a representation of the semantics of the word itself. So as you saw here, you can do tasks like this. You can take the vector for Berlin, and you can look at it in the vector space, and the entries that are close to that vector for Berlin are things that are similar to Berlin. This isn't a perfect system. It sort of, there's cases where that breaks down because you have, so okay, before I go into that, does that answer your question?
I think so.
Okay.
So with this 300-dimensional vector space, where the rows are the words, okay, you could just do a cluster analysis on that, right? And
Yeah.
find all the state or all the capitals of all the countries should be similar to Berlin.
Yes, you would hope that all the capitals are similar to each other, but that's not always the case. That depends on the data that you feed into. But you could absolutely do clustering that, like, there's all kinds of neat applications for word vectors that aren't as such related to neural networks. But you can do cluster analysis, you can do all kinds of analysis of word usage over time. How was how has the meaning of particular words, how has that changed over the centuries? Because these vectors allow you to capture somehow that contextual information.
I wonder for the similarity, like in what sense is it similar? Is it like semantically, or is it like just by the distance based on the word track? Because I'm
Right. So in what way is it similar? This is the crucial point. It's not similar semantically, except that in a strict sense, the similarity is measured in a vector space, specifically as the cosine distance between the two vectors. Right? So it's a geometric similarity measure. But the entire point is that geometric distance between the vectors is representative of the semantic distance in the human space. Does that make sense?
maybe half. But like I'm thinking about the adjectives where apple means the fruit and then apple means the company Apple.
Right. Okay. So I wanted to come to this. So there's absolutely cases where this just breaks down. So you have things like antonyms, opposites, good and bad. Depending on what exactly you want to do, they're either the opposites of each other or they're actually very similar. But if you think of it in the sense of like the context in which good and bad are used, we can take a good apple, no, a bad apple, that's not a good example. This is a good presentation and this is a bad presentation, right? You can substitute one word for the other without changing the context. But the word vectors capture the context, or they represent the semantic meaning of the words through the context. But because you can substitute those words, good for bad, it means that often you'll end up having a similar representation for good and bad. I don't know if this is going to work. Let's see. This is the English. Okay. Ha! Right? Does that make sense? Because they are if you just think of sentences where you would use these words, you can replace in that sentence often, not always, but often, good for bad and the other way around. Of course, you change the semantic meaning of the sentence, but it's a valid operation to do. Whereas I can't replace good with cauliflower, right? That's kind of the idea.
Just to prove that this approach is not perfect.
No approach is perfect. No, but it's a really, really good point. Like you absolutely have to keep this in mind when you're working with these. That they do not capture the sort of our understanding of words, or they don't capture the same information about words that we have. They don't, they're very they're very neat and extremely useful, but they're not a universal thing.
I was just going to point out that if you use the German word, it's a nice example because if you use the German word for good, Schlecht also pops up, right? So like,
Yes.
so it's similarly, they're making the same analysis of the two different like corpuses.
Yeah. Yeah. This is later in the end of this thing, we're going to get into contextual word embeddings, which then changes this dynamic. Okay. Other questions? Cool. So recurrent neural networks. I think I need to go back to my slides for this one. Recurrent neural networks. So this is a very simple recurrent neural network. So the idea is, in the previous example, we had a fixed length document that we either truncated or padded, turned into vectors and fed that into the architecture. Or of course, documents are not fixed length. They have varying different lengths. So the idea is that you can capture that. You can capture these sort of sequential models that, or sequential data that may or may not be infinite with recurrent neural networks. So you go through your input one item at a time. And the way this is done is usually through some kind of internal representation. Oh, that's awesome. Internal representation that, or internal sort of state that the network maintains throughout that data processing. And so what we have here, this is a simple recurrent neural network called an Elman network. Here's our input coming in, and here's the hidden state from the previous time step. These two, the hidden state from the previous time step and the input, are integrated together through a non-linearity. There's this orange box here contains two sets of weights. There's one set of weights for the inputs. That's a trainable parameter. There's another set of weights for the hidden state. That's another trainable parameter or set of parameters. And then these two are sort of put together to create the new next hidden state that is then passed on to the next iteration of that recurrent neural network. And then from that hidden state, you also produce the output through yet another nonlinearity, and there's yet a third set of weights there. This is not what people actually do. Here's an LSTM. It's much more complex. So you have the hidden state. The crucial idea here is that in the Elman network, you just have one hidden state. In the LSTM, you have this hidden state, but you also have the cell state, or like a contextual information. This contextual information, this cell state is the thing that gets updated. You have 3 gates. There's a forget gate. So from the previous time step, we take what the context was, what the cell state is, and we apply an update to it. This is essentially saying, what is it, given this new input that is coming in, what from the previous time step do we need to erase? What is information that we can forget? That gets passed onwards. And then there's an update. There's an addition here. The update is essentially sort of doing the similar thing. It computes 2 things. What needs to be updated? Which positions in this internal cell state vector? Which positions need to be updated? And by how much do they need to be updated? Is it a +1 or a -1 or a +0.2? And so on. These two are again put together. Yes?
Why are 2 different definition functions used?
So these sigmoid functions range between 0 and 1. So they either like think of it, you can think of it as a binary thing where they either completely forget something or they completely keep something. And this tan h is between -1 and 1. So it either sort of reduces the activation of that position or it increases the activation of that position. But that's why you have two different functions to get those two different ranges. Right, and then you do an update of the internal state and again pass that on to the next time state. Yes?
Do they ever use a ReLU instead of a sigmoid?
Yeah. Rectified linear units are used. Although, so this is the definition of the LSTM cell. I think you can use a ReLU like in between cells if you stack them together, or other sort of activation, non-linearity as well. It's not super important that you understand the exact specifics of how this works. The main idea is to kind of, well, one, it's a relatively complex thing, but the fact that you have this context that gets sort of, something gets forgotten from the context and then other things get added to the context, they allow the LSTM cell to carry information over much, much longer distances in the sequence than this simple Elman network. Is that sort of roughly okay? There's a whole bunch of details on LSTMs. This blog post, if you really want to know the exact details of how LSTMs work, I recommend the blog post by Chris Ola. It is very approachable, but also very detailed information. And there's a whole bunch of extensions and blah, blah, blah. One thing that I should say, so this bit here specifically, there's a discussion, perhaps I could say, going on in the NLP community that sort of between the new kind of transformer models, which we're going to look at next, and these recurrent models, that because language can be seen as a sequence, you must model language as a sequence. And it's not clear if that's actually the case. It has been the case before that like these have greatly improved performance at various different tasks, but it's not clear if it's actually necessary to model language or text as one word following another word. There's some psychological evidence that that's actually not how humans read. And there's also empirical evidence from just neural network research that, well, actually you get better results if you don't do that. Do something else. This paper is one sort of starting point for looking into that. Blah, 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 blah. I've kind of said all of this already. That's the Elman network in practice. Okay. So this is going to take a little while to run again. Let me just see where I can skip to. So the idea is that we're basically doing more or less the same thing as before. We load the German word vectors. So let me just actually close this, free up some memory. Where is shutdown currently? Okay. Load the German word vectors. We turn the vectors into indices. We have the embedding layer, and then in PyTorch you have an RNN implementation, which is the sort of base RNN implementation. That's just an Elman network, and you can feed the vectors into there. You have some sentence. You create word indices out of that. Sent is not defined because it is not called that. And here we go. There's a bunch of entries in the word index table. This is what you get out of that operation. This operation. Right, so we're turning the words into just individual index positions. You run that through the embedding layer. But notice that we now run the entire sentence in one go, and you get one output position per sort of entry in the per word in the sentence, right? This is the recurrence kind of unwrap. This is actually just the embeddings, right? So this is now looking up what the word embeddings are. This is whatever, 6 by 300. And then you run this embedding through the RNN, and we get something that is 1 by 6 by 10. I think I said somewhere that the internal, yeah, here we go. So the output dimension of the RNN is 10. This is exactly the kind of vector that you get out of there. The hidden size is the same. This is what the output looks like. That's what the hidden size, the hidden state in the Elman network looks like. Okay. Are you okay with this this idea of just passing in a bunch of data and then the network internally doing the recurrence? Okay. What did I call it? Small? No, I already loaded those, didn't I? Yes, very good. But I called them something else. So let me change that. Okay. We add the unknown. So there's going to be words in our data set that are not in the pre-trained word embeddings. So we add an unknown vector, which in this case we just set to a random thing. Then we create a somewhat strange training loop. Right. So what's happening here is we go through every single document and we feed every single document one by one into the recurrent neural network. I'm not actually going to run that because it takes quite a long time. But the idea is exactly the same that we do. We sort of take our data, we feed it through the network, we measure the loss, blah, blah, blah. You've all seen this before. Now, this is the crucial part here. You can do this, right? We don't need to do anything to the neural network architecture itself, how it's defined, in order for us to feed inputs that are of varying different lengths. It is completely happy to just accept documents that don't all have the same length. However, this is very inefficient because we're having to iterate through every single element, every single document in the data set one at a time. If we're using a GPU, which you are going to need to for this kind of a thing, you need to move every single document one at a time into the memory of the GPU and then back out again, and then the next one and then back out again. That slows down your training. Batching the documents together is not possible, not because the network wouldn't accept those, but because the internal sort of machinery of PyTorch will just say you can't create a matrix where the entries are of different lengths. So we have to do something about that. This is the only thing that's like really PyTorch specific. However, other frameworks like TensorFlow will have the similar thing, but it's not called exactly this. So the idea is that we do we compute the lengths of the documents and we pad everything to the length of the longest document, or you can truncate if you want. And now our data set becomes like this. So these are now, I think these are like 3,000 something long vectors, where for most documents, most of the entries are just 0. And then we can do that. So you take in the mini batches that you're taking, you take the documents and the document lengths, which you're passing in here, and you pass that to the PyTorch machinery. It'll create a matrix that is just big enough to fit your documents, and then pass that matrix into the network. What you get back, this X size from this output, once you've passed it through your LSTM cell, is not the original 3000, but it's whatever the shortest document was in that batch. This can trip you up if you're not careful. Okay, then there's a whole bunch of stuff that we can do now with LSTM. So now we have the machinery to run some documents through an embedding layer, through an LSTM, and sort of batch everything together and run the mini batches and so on and so on. And then there's a bunch of stuff that you can tweak, where you can tweak the parameters for the LSTM cells. We can change the hidden size representations. How wide are the layers in the LSTM? Or how wide is that context vector? How much information essentially are you allowing that context vector to capture? How many layers? Is it a bidirectional LSTM? So a bidirectional LSTM will concatenate the representation of a forward pass and a backward pass through your over your data. We add a classifier. So you have an LSTM cell that outputs some kind of a representation, and then you have a linear layer that takes that representation and outputs some number of classes. Right? We're still doing the same document classification task that we were doing in the previous thing. So we have 9 classes, but the LSTM just gives us, if you want, an embedding of the document. Now we feed that embedding of the document or documents into a linear classifier layer that then outputs our class probabilities. And then we have some optimizer parameters, the optimizer, and so on. Number of epochs, and again, you can see this is more or less exactly the same as all the previous examples, but here is one crucial point. So we run the data through the LSTM. Now, if you remember, the LSTM gave us a representation for each word in the document. The question is, what do you feed to the classifier? So in this case, what we're doing is we let the LSTM run through each document all the way to the end, and we take that last hidden state, hoping that that last hidden state captures the semantics of the document that the LSTM has just seen. And that last state is fed. Only that last state, not the previous states, only that last state is fed into the classifier layer. What this bit here is doing is exactly that. It's just indexing out of that LSTM output. It picks out, for each document that is of a different length, it just picks out the last state of each of those documents. And then you pass that to the classifier, and then you do some bookkeeping. And this is where we get into a point where I can't actually run this anymore. I can check that it works. It seems to. Very good. Right, so now the question is, well, how does that do? So I ran earlier some sort of benchmark comparisons. Thank you. Some benchmark comparisons on what happens when you start fiddling with those parameters. The hidden size, is it bidirectional? How many LSTMs are stacked together? And here we have some results. So the hidden size is 64. It's one layer plus a linear classifier, 100 epochs. That's the optimizer. That's the amount of time it took to run on an EC2 P3 GPU instance, and this is what you get up. So overall F1 score or accuracy is that. Here's micro and weighted F1 scores, right? If we just focus on the accuracy 80%, then we do what is different optimizer. Same amount of time spent, we get a little bit better performance. This changes obviously if you change how long you run the LSTM or that training. We can increase the size of that hidden representation. We've now doubled the the information content of the LSTM, of that internal representation. We've added a second layer. So now you're not passing that initial output that you get from the LSTM that consumes the input is not going to the classifier, it's going to another LSTM. So you have two of them on top of each other, kind of working together. And again, you get slightly better performance. But you've also doubled your training time. And then you can do, oh right, okay, so here's an interesting question. What's better? Deeper networks or wider networks? Or deeper and wider? Depends. The community is sort of verging on deeper, but it's not clear to me exactly why. There seems to be some evidence suggesting that it's better to have deeper networks than it is to have wider networks.
There's a way to see, like, at some point it doesn't improve anymore.
Yeah.
Doesn't matter how many layers you use, right?
Yeah, so obviously if you have the time and the money, this, like the last one took 17 minutes, so a bit over an hour. You can keep going and like spend a couple weeks running these experiments and then you'll have your answer. But but yeah, so here you can see, so the 2-layer 128 width LSTM, we get 85% accuracy. A 4-layer LSTM with slightly smaller internal representation state, we get slightly worse, not exactly, right? Questions? Let me see, is this actually running? Yeah, this training is working. But I'm just gonna stop this because I don't think we're gonna see any output from that during this presentation. Questions? Have I lost everyone? Is that why you don't have questions, or I'm just going through this so thoroughly that I've already cleared all questions? Yes?
I just was wondering if you might clarify the linear classifier and what that layer is.
So the linear classifier just takes that last output from the LSTM and has a linear layer, which, so hold on, what is it? A fully connected layer,
Okay.
which takes, so the LSTM, hold on, the LSTM size here is 64, but we have 9 classes.
Yeah.
So that fully connected layer just translates this 64 to 9.
Yep. Okay. That's what I thought. So linear is sort of a synonym for like a fully connected.
Linear, yeah, fully connected, but
To
also
the-
there is no non-linearity in there. Right, so if you think back to what the LSTM has, there's a whole bunch of different activation functions and blah, blah, blah. The linear layer is just, you multiply a set of weights with some inputs, that's just a linear function. Other questions?
How bad does it get when you don't do bidirectional?
That's not bidirectional.
Oh, okay.
This is 82 here.
Does it,
But like this is 64 and 1 layer, and then the bidirectional is 128 and 2 layer. Yes, I didn't do proper kind of analysis.
but the other one above it is bidirectional 1 layer, right? Oh no, this. Okay.
No, these are both one layer, but you have a different optimizer. The GPU instances on Amazon, the hourly price looks a little scary, but it's not. I mean, this all together took less than half a day. So that's like, I don't know, $10. So it's not like, I recommend that you go and try. It's not that expensive. It gets expensive when you start running the really big GPU machines for a couple of weeks to train like really big networks. Sure, that gets expensive. But just sort of playing around with this a little bit, you're fine. I actually tried, so Google Colab has GPU instances that you can use for free. You can take these notebooks and just upload them to Google Colab. And they have GPU instances, but it wasn't like, they worked okay. It wasn't particularly fast. It's faster than running it on your laptop. You can always cut down the size of the data set, for instance, if you just want to play around with that. That comes at no upfront financial cost. It'll just cost you time. Right. So then I'm going to sort of skip through a couple of ideas. I'm starting to run out of time, but I'm going to skip through a couple of ideas. There's no code here. This is just sort of giving you some kind of an overview of where we're headed, what I think it would be useful for you to be aware of. So sequence-to-sequence learning and the encoder-decoder architecture and attention. So sequence-to-sequence learning, the idea is that you have, this comes from sort of the machine learning, machine translation area. So you have a sequence in German and you want to translate that into a sequence in Finnish. Those two sequences don't necessarily have the same length. So the idea is similar to what we did before, where you have an LSTM or two stacked on top of each other or four stacked on top of each other that create some kind of a representation of what the content is that was just consumed. You have a different thing, that linear classifier that we put on top, that then consumes that output, that embedding, that representation. Now, the encoder-decoder architecture, the idea is the same, but instead of having a classifier, a linear layer on top, you have another recurrent neural network that consumes that final hidden state. So you have one RNN, one LSTM, that produces some kind of an embedding of the input, of all of the input. You have a second one, the decoder, that given that embedded state, decodes and produces a different language or, I don't know, some other output. The problem, the somewhat obvious problem here is that you're putting an immense burden on that hidden representation to capture accurately what the input was. This is where the whole attention business comes in. You can use attention to, so the attention sort of gives the decoder network has a way to compute how important were the words in the input sequence for the output that the decoder needs to be producing. So it gives the decoder a kind of a weighted representation of the input, essentially. There's a bunch of stuff here that where you can go, like this article there's a really, really long and detailed article about different kinds of ways of applying attention. That's the original paper. This illustrated attention is maybe a good place to start because it, in a very kind of nice pictorial form, goes over what the idea behind attention is. I always find pictures to be extremely helpful. There's also a PyTorch tutorial in the documentation itself, specifically on machine translation with attention. So you can go and download the notebook and then just look at it for yourself and run through it. Right, so now we get to contextual embeddings and transfer learning. Okay, did you have a question? Okay, contextual embeddings. So the idea is that, this is not charging my laptop. I'm gonna run out of battery soon. Panic, panic, panic. Okay, why is this not on? I need some way of charging.
That's why the battery.
No, here you go. Oh, are we charging? No. Okay, that's scary. Maybe my laptop is broken. Ah, okay, good. We're good. So, contextual word embeddings. So the idea behind contextual word embeddings is that these word representations, these word vectors that we had before, they were static. You just had some corpus, some data, you learned them, and then that's it. But the meaning of words, it changes depending on the context in a dynamic way. As an example, so as I said, I live in Berlin. Where's my mouse? There we go. I live in Berlin. I actually do live in Berlin, and I actually do usually cycle to work. But I also work for a travel tech company, so what we're interested in finding is we want to find, for instance, the origins and the destinations of flights that people want to book with us. So we need to be able to identify whether some mention of a location is the origin of a flight. Now, clearly, I live in Berlin and usually cycle to work, and can you book me a flight from Berlin to New York? In both cases, Berlin is a location, but only in the other case is it the destination, the origin of the flight. So that meaning of the word in this specific context is dependent on the words that are around it. This brings us to contextual word embeddings. So now the idea is that you don't just create a fixed lookup table for the word embeddings, but you actually have some machinery that is part of the network itself that you're running. And that integrated machinery, as you are learning, but also at prediction time, it actively computes, it creates these word embeddings as just part of what it does. Does that make sense? There's a bunch of different ways of doing that. You've already seen one, the LSTM that we had before. The output from the LSTM can I find it? Ha. Right? You have one hidden state per word. You could, if you wanted to, say that that hidden state at that position for that word is a contextual embedding of that word given what surrounds it. And this is exactly the idea that people have then taken and sort of carried forward. Again, here's a bunch of research papers introducing that. This paper kind of introduced in a very significant way the idea of transfer learning to neural networks. So from these contextual embeddings, we get to language models and training sort of deep networks that have integrated not just the ability to create contextual embeddings, but have actually hopefully learned something about language in general, and then we take that entire network architecture and we transfer it to a different task. Usually these are trained to be language models first. So the idea is to just be able to predict what the next word in a sequence is. But that task allows the network to capture some kind of sort of inherent properties of language itself, which are then useful for whatever your final task is, in our case, document classification. And again, the idea is exactly the same. Whatever that language model large network architecture is, you take that and you put a tiny little linear layer on top as your classifier, if that's the task that you're doing. There's a little playground area here for playing around with a pre-trained language model. You can actually use it to generate language as well, but I have 15 minutes of time left, so we're not going to do that. The mighty transformer. Okay, so the idea here is, I gave away the joke already. So these word embeddings, right, they're very useful because they allow you to compose together word meanings. So you can take the representation of red and you can take the representation of car. Now you already know what the joke is. You get a red car. You put them together and you get a red car. Maybe you add them, maybe you multiply, who knows? That's not the only way of creating word representations. You could also create word representations that capture various different sort of grammatical relationships between words. So we have a lovely group here. And there's a lovely is an adjectival modifier of group. We can use this information to create a representation that specifically targets this kind of information. This is a bunch of research that was done at the research group where I did my PhD. This is not my research, it was done by my colleagues. So the idea is that you go through a bunch of data and you extract this adjectival modifier and all of these dependency structures. You create a big graph out of that, and you can now say that, well, music is anything that is related to it. So music can be lovely or blue or loud, but the representation for music is the network structure within which it exists. The point that I want to get across here is that word embeddings is not the only way of doing this. It just happens to be very convenient for linear algebra, because these network structures are very difficult to add together and subtract from each other. There's also the kind of what I said earlier about the language models, not language models, but these recurrent neural networks and language being a sequential structure, and you having to sort of represent or model language as a sequential structure. There's this NLP's Clairvoyance moment kind of, it gets to the point that the transformer architectures that I'm going to talk about next, they learn things about language that we're not entirely sure what those things are, and it's not clear if those things are representative of linguistic structure in general. That it's just learning some sort of patterns that happen to be useful given the data set that you have. But I work as an NLP engineer. I don't particularly care if the network correctly represents linguistics. And if it depends on what you're applying those methods to. But it's completely okay to use methodologies that are not necessarily accurate linguistically, as long as they actually improve performance at the task that you're trying to achieve. Why do you care if it represents language correctly? It improves performance, period. Right, BERT and the transformer. This is the transformer architecture. we're just going to ignore the other part. So this is a beastie beast. There's two parts to it. One is the encoder. You've already seen an encoder in the LSTM. The other one is the decoder. But BERT, which I will actually talk about, doesn't use the decoder. It just stacks these encoder bits on top of each other. And I'm going to talk specifically about two parts. One is the input embeddings, how you feed data into it. The second is that multi-head attention. So the idea behind this transformer is that instead of consuming data sequentially, which is computationally inefficient, you have to consume one thing after the other. That puts a constraint on how fast you can actually process data. Transformer just slurps in the entire sequence in one go. But now it's not clear anymore how do you represent that contextual information that you before in the recurrent neural network architecture were capturing in that context state that was updated after each recurrent step. Okay, but first, the input embedding. So the transformers and a lot of other neural network methods nowadays as well, they use something called a byte pair encoding or subword tokenization. So they will split words into sort of just some sequences of characters that may or may not be complete words that we as humans would recognize. Why would you do this? So I am a native Finnish speaker, and here's a couple of examples of how Finnish works. We don't have prepositions, any. Finnish creates meaning in words by just sort of adding stuff to them. So here's a word, ajaa, to drive. Here's the imperative form of that word, drive. Here's a driver. Here's someone who makes the driver drive. For instance, the passenger in a taxi. Here's the boss of the taxi company making the taxi driver drive. It's a weird language, but it's also a wonderful language. I recommend that you all learn it. Any native Finnish speakers? Anyone? No. Right, you can also do this. So you can say sort of, if I should casually drive. And now, because you're all hyper intelligent people, I'm sure you can all tell me what this would be.
Kohan?
No one?
Is it Kohan? That's the last bit? KOH.
I forgot.
Oh, sorry.
Yeah, it should. Yes, it is. The last bit is Kohan. Well, no, it isn't. Yeah.
No, it isn't.
Okay. But I hope this sort of motivates. And I admit that, yes, Finnish is an esoteric language. But Finnish isn't the only language that does this. There's similar effects in German. There's actually similar effects in English as well. You have describe and prescribe, right? Those are prefixes that change the meaning of scribe. You don't usually think of them as prefixes, but they are prefixes. Okay, right, so that's byte pair encoding. It doesn't work, like the system doesn't split things into neat kind of prefixes like pre and D and so on. It's a data-driven approach to tokenization, and the BERT model comes with its own tokenizer. So now the question is, right, how do we do the contextual encoding? So this transformer architecture, or this like bit that you saw before, these encoders, they are the things that do that contextual encoding. How do they do that? Well, this is roughly how they do that. So we're interested again in the representation of Berlin. But now we want the representation of Berlin to include the context that we have here. So what the encoders do is they allow each of these words, or to be accurate, the word vector of the subwords of each of those words, to have an influence on the final representation of this target word. So there's a bunch of sort of weightings that are computed in those encoder blocks that then finally create this representation, right? Notice that these numbers are different to these numbers. This is meaningful, it is purposeful. Because the encoder that sits here in between has taken the representation of all of this and sort of folded it in to the representation of the target word. The way this is learned is they actually do a masked language model task where during the initial training phase, the network needs to be able to predict from that context what that middle word is. That some words are randomly masked out from the sentences, and those masked words, those deleted words from the sentences, need to be the output of the network for that particular iteration. Notice that this is very similar conceptually to the skip graph model. No, from the continuous bag of words model, where from the context, the task is to predict what the word is. Let's do the code. Okay, so 5 minutes left. We're not going to do any code. Original paper, here's a bunch of really, really good, very detailed, very approachable articles on the transformer model. There's a lot of work right now being done on model compression, because these are ginormous things. So it would be useful if we can run them on compute hardware that isn't quite as expensive. There's also a bunch of problems with interpretability. The claim is to some extent that these attention weights that the network is learning can be used to interpret how the network is actually doing its prediction. But then there's also some research saying that that's not the case. Subword tokenization. Hold on, let me just see if there's something that you really need to know here. I mean, you can take all of this and just run it later on your own. Maybe this, can I run this on its own? No. Need to load everything. Okay. The idea here was to show what the different learning rate schedules do. So I talked right at the beginning that at first you have to, or you want to have a really, really low, small learning rate, so that the updates, when the network hasn't seen a lot of data, the updates that you're doing are very small, and then they gradually increase. This is just plotting that. Document classification. Again, the idea is exactly the same as we saw already previously. You have this giant network architecture and then a tiny little document classifier linear layer that sits on top, and you let the network do the encoding of the text, and then you just use that in your final prediction task. There's a couple of different ways you can do that. There's two examples here. You can either adjust the weights of just that final classifier layer, which turns out not to produce particularly good results. Right, before we had accuracy around 84, 85. But you can also just open up the entire transformer stack, the complete network architecture, and just optimize everything. And then you get much better performance. No, this is wrong. This should be 85, not 55. Okay, I need to correct that. And then this is finally a linear SVM that runs on a laptop in like 3 months.
So linear SVM did better.
Yeah. This is not, so for document classification, I'm not sure if these like large transformer architectures is what you want to go with. But we use this in production where we do word level prediction. Well, basically what I showed you before, that like is Berlin the origin or a destination or neither. We use it for that kind of thing, and this is way better than anything that I've tried thus far. Anything else? Okay, I think that's it. And I'm also out of time. Questions? No questions. That's a bad sign. Okay, thank you for listening. Oh. One thing I forgot. Because these networks are so large, they also consume a lot of energy. So there's another bunch of research that's currently being done is on sort of creating, first of all, measuring the energy efficiency, but then also creating models that are computationally not quite as expensive. There's a workshop proposal for the 2020 EMNLP on kind of sustainable NLP. So these models you need a GPU for, but the field as a whole is sort of coming to the realization that we're not entirely sure if that's necessary. Let's try to find some slightly less computationally expensive things to do these things with. Finally, I want to thank a bunch of my colleagues who helped in creating this, Andra, David, Mark, and Tobias. They were extremely helpful in providing feedback for this, and I want to thank my employer for actually allowing me to come here. Thank you all.